In this video, we are going to see the working mechanism of organic photovoltaics. The general working mechanism of organic photovoltaics is little bit different from the conventional photovoltaic devices. So, organic photovoltaic consists of the following layers: anode, cathode, transport layers, electron transport layers and hole transport layers, acceptor and donor materials. So now we will see how this solar cell works, and before going to that we will see what is the role of each layer in this. So we have as usual cathode and anode. It is like any other electronic devices, one for the basically positive electrode, another one is for the negative electrode. So then we have a transport layer, so electron transport layer, and on the anode side we will be having the whole transport layer. Sometime we no need to use, but for the efficient device efficient high efficient devices, these transport layers are used. So apart from that, acceptor material and donor material, which is basically will act as a semiconductor layer. So here the donor is a kind we can it's a kind of equivalent to the p type, and the acceptor which is equivalent to the n type material in the conventional photovoltaic devices. So these donor and acceptor materials generally dissolved in the solvent, and then we will be making as a layer, and then the anode layers. So upon the light illumination, what will happen is the following. So once the light is passing through the devices, the exciton will generate. So that means the exciton will generate in the donor, which is basically the polymer, and the acceptor, which can be small molecule like the fullerenes or some other polymer materials. So once the light is entered in the organic solar cells, the exciton will generate in the donor materials. So that means the light will be absorbed by this polymer, which is semiconducting in nature, and also the light active semiconductors, photosensitive or photoactive semiconductors. So the light will be absorbed by the semiconductor and exciton generation will take place. So generally the exciton which forms in this kind of organic materials like small molecule or polymers, they will be the Frankel type excitons, and that basically means that Frankel type excitons are having larger the binding energy than the regular March this Vanier type of the excitons. So what happens, these since these excitons generated in the polymers are Frankel type, and which are high binding energy or tight binding, they are having a tight binding energies. So they required the four external forces or the potentials to drive these bound state of electrons and holes into free charge carriers. So exciton basically we know that it is a combination of or the bound state of electron and holes when they are tight enough, and they are not getting split into free charge carriers. So that is because of the tight binding energy of these excitons. We need to provide them some external energy or some means in order to dissociate them to get into free charge carriers. So only if you are splitting these excitons into free charge carriers, we can able to generate the flow of the currents or generation of or the charge transport, and hence the current. So therefore, in order to provide the potential difference, or in order to break these excitons into free charge carriers, so we are providing adding additional material which is actually called as the acceptor, As we already told you, this is actually it can be the small molecule materials or small kind of the fullerenes or some polymers. So since this energy difference, the homo energy difference between the donor and acceptor will be acting as a driving force. So generally when you choose the acceptor, so the highest occupied molecular orbital, that is HOMO level, should be lower than the HOMO level of the donor. So this kind of energy difference, you know, drives these exciton into the free charge carriers. So that means this potential difference between the donor HOMO level and the acceptor HOMO level enables or drives these exciton into free charge carriers, or breaks the free exciton into the free charge carriers. Once these free charge carriers are broken, what will happen? The electron will be moving towards the cathode because of the energetically favorable layers that we are embedded in the devices. Similarly, the holes will be moving towards the anode. So this kind of free movement of charge carriers after the light illuminations will basically results in the current generation in the photovoltaic devices. Now we will just see this animation. So after illumination of the light through this on the donor polymer, the excitons are generated, and we can see this dotted line basically means these electrons present in the LUMO level of the donor, and then the HOMO level of the acceptor, HOMO level of the holes present in the HOMO level of the donor, which are basically not freed, or they are having some coulombic binding energies, right? So therefore what happens, these once they are moving towards the interface of the donor and acceptor, so they will get into they split into free charge carriers. So because this splitting of the free charge carriers, because of the energy offset between the LUMO acceptor and LUMO donor. So because of this energy offset and charge transfer will takes place from donor to the acceptor LUMO, and then the charge carriers will move in the following manner.